Hi, in this video, I'm going to introduce the implementation of a stack based on linked list. Now, we did implement a stack previously, and that is using an array. So specifically in our assignment, we use the NumPy array to allocate space for the storage for items that we put in a stack. So what's the problem with that? Well, there are multiple problems, but mainly it has to do with the fact that the array is a fixed size, right? So we have to we are given a capacity. So whenever somebody wants to use a stack, it has to know how many things it wants to store in the stack. So what if we don't know that, right? But now, assuming even if we have some sort of idea of that, we then have to allocate all of them up front. Now, what if in reality it turns out that we don't need as much as we thought, or we are using a lot more than we initially thought we need, right? So there are all sorts of problems with the initial guess of at the capacity is not quite correct. Now, before we make this modification to the MyStack, we were using actually a Python list to store all the items we want in a stack. And we know that Python list can grow, so we can just grow it as we need more spaces. But that kind of begs the question, how does Python list grow, right? We still want to understand how these things work. So whether we're using Python list or NumPy array, we now want to learn how to dynamically allocate more memory and keep track of it as we need more of it. So the fundamental question is, okay, we have a block of memory, such as that allocated by a NumPy array, and we put data in it. And as we want to put more data into it, why can't we just make the block of memory bigger? And that has to do with how spaces in computer memory is allocated. Now, this is a very, very simplified view of what a computer memory looks like. So it's basically a giant array, let's say, of just spaces. And as we go through our code and execute them, then blocks of the memory is going to be allocated, it's going to be used to hold the data that the code need. So for example, when we do this self.stack and assign a NumPy array to it, space is going to be allocated for the NumPy array. So a chunk of it is going to be carved out from the memory, and our Python interpreter is going to remember, okay, this chunk of memory has been used for this particular attribute. Now, as we execute more and more code, the space around the self.stack is going to be occupied by other code. So when we need to grow an array, a block of memory, we might not have room to grow because the spaces around it has been taken up. So then what happens is we might find spaces in other parts of the memory, but it's not going to be at the same place as the original um, data. Now, then the question is, if we have these blocks for our data just all over the places inside our memory, how do we keep track of where they are? One way you might think of is that we can allocate a block of pointers, and each of these pointers would point to each out of our blocks that store the data, right? So for data that's broken up into two different blocks, then we need two pointers, and each would pointing to these two blocks. Now, there is a problem with this though. Can you see it? Well, the problem is, well, this block of memory, this block of pointers, they also have to live somewhere in the memory. And as we allocate more and more blocks of data, this block of pointers itself also has to grow. We are back to our original problem that we still need to find a way to grow this block of pointers. So an alternative or a better way to do this is, instead of using a separate block of memory to store these pointers to the block of data, we would take a little bit of memory in each block of memory that stores the data to store a pointer to the next block of memory that stores our data. And then again, for this block of data, we'll take a bit of room and store another pointer that points to yet the next block of memory that stores even more data. And in this way, we can, if we need more blocks to store more data, then we can just keep allocating more blocks, and we just keep chaining up these blocks with a little pointer that is embedded in each of them. So in this way, using this chain of memory blocks, we can store as much data as there are spaces in the computer's memory. So at a logical level, and more formally, this is what's called a linked list. And it's a data structure that is very, very useful, very flexible, and very well studied in computer science. As a matter of fact, there are computer languages that are based on the idea of linked list. But anyway, at the very basic level, linked list has a bunch of nodes, and each of these nodes stores some sort of data, and all of them has a pointer, typically called the next pointer, that points to the next node. And then a number of these would then point chain or a linked list. Now, there are variations, actually, as a matter of fact, many different variations on this idea, but they all share the same basic structure.